All right, so for anybody who has it up, can you see if you actually have the broadcast going? So just probably bring it over a little bit. Can I get confirmation from somebody that it's running? Yeah, that's it. Yeah, it's running. Oh yeah, you just press if you get out there and press refresh. Yeah, that would work. The link that I just sent in the class. The first part. And if you don't have a laptop, just share with somebody who does.
I don't know, I'll just share. My battery just goes down.
Well, that's same.
My battery just goes down in like no seconds.
You can't have internet anymore?
Mine doesn't shut up. Mine is not.
All right, so for those of you who do have laptops, I think we've got a few people who don't have one available, so if you'd be so kind as to either share or, okay, so I think, does everybody have? All right, so, yeah, if you could press mute for the time being, so that way I just don't hear a lot of, like 7 or 8 versions of me talking back. For a while, then the hallucinogens set in, and then suddenly that's the day that Dr. Morrison started fighting the dragon. Yeah. Yeah, see if you can, yeah. All right, so while Josh is figuring that out, so everybody remembers why this wasn't a this was an error. Correct. Yeah, so this particular here, you can't have them overlap like that, because what's going to end up happening is you can either, it will simultaneously go this way and this way, which means the actual logic of this circuit is if there's any path, if it's activated at all, regardless, it'll always go through. So that is bad. So here's the one that I asked you guys to do. Now the question is, all right. There's the word you got now.
But I thought this class started at 9:30. So I was like,
Nope, it starts at 9. What's that? You have a laptop on there. You know it. That's okay. Well, either way, I'll put it over here. All right. So while Josh is finishing that up, let's go. I want to go over the example question that I gave you guys. So the question is, it's F equals quantity A, B, or D, C, or E, and it is negated. So first we want to deal with the, so the way I presented it last year with De Morgan and no De Morgan, the way I've taught you guys is with no De Morgan's law. So when you had to do the pull up, remember that ands are in parallel or ors are in series. So you start out with and, so you go, this would be input A, input B, and then it's in series here. Now, what's going to happen is, because this is ANDed and these are ORed, these are going to be in series, and it's going to be in parallel with that. It's going to be in series with these guys. So what's going to happen is, you're going to have D over here, and this is a Pmos, and then you're going to have B or C, and E here. And so that's the pull-up network. Does that make sense to everybody? And so opposite, so this is going to be V out. And so the opposite way is now you worry about when it's the pull down network, ands are in series, nors are in parallel. So what's going to happen is these are in parallel. So first thing you're going to have to do is you're going to have A and B in series here. Does that make sense? And then you're going to have D. It's going to be here. And then you're going to have in parallel C and E. And E is going to be parallel. Any questions about that?
I have a question.
Sure. I mean, we haven't gotten to the stick diagram yet, but yeah.
For the pull-up, would it be still the same circuit where if you added B, C, and E flip-flop?
Oh, you mean like this? They're just like that?
Yes, literally on top of it.
Yeah, no, it's the same logical circuit because this is okay. So this is a good question. So the question is, if I put this portion of the circuit here and this portion of the circuit there, is that the same circuit? And the answer to that question is yes. And the reason why is because ultimately everything revolves a logical and valid path from VDD to the output. So in order to, let's say I have A is 0 and D is 0 in this circuit, right? So if A is 0, means it's going to go through here, and then D is 0, is going to go through there, right? Now, if they're flipped, as you asked, that means it would go through D first and then A.
Okay. So it's still the same line.
Correct. Does anybody have any other questions? All right, so the next part is stick diagram. So the stick diagram is coming up with your path diagrams, which is essentially just, actually I can zoom in here a little bit more. So from VDD, we had 0 and 0 to the output. So we get a 0 and 0 on A allows us to get a 1 on the output. So this is the same thing. To answer your question, if we did VDD and this went D, C, and E, and then A and B, and that goes to the output, that is the logical equivalent of a flip circuit. But it's still physically, it'll still give you the same physical results because you're going to have D and then A, whereas it would just be A, then D. Or if you had, in the other case, if you had, it would be B is 0, and then C and E are 0. Then you get a logic on the output. In this case, it would be C or E, or C and E are 0, and then B is 0. But it gives you the same result. And then for our pull-down network, it's C or E and D, or B and A, or A and B. So now we have our path diagram. So then what we need to do is we actually need to draw our P diffusion, N diffusion regions, our V out, our VDD, and ground. So this is our resulting circuit. So we just use the same paths here. We're basically creating a metal path from VDD or ground to the output. So to correlate our pull-up network with metal, we're going to go through this and show you how it actually works. So VDD, let's say I wanted to do A and C and E, right? So if I first do A, right, what's actually happening is we go from VDD, it goes through the A transistor from the source to the drain, and then it's going to circumvent B because you don't need to worry about it. Now, in order to get to the output, which is here, this path, I either need to go through D, which would be, in that case, going through here, or I have to go through C and E, which would be like going through that. So it has to do one of those two. So basically what's going on here is I am circumventing the D transistor and I'm making sure I go through C and E, like so. Now, if I had B and D, the way this path would work is it would start here, I'm in VDD, I go through the B transistor, that's source to the drain, and I go through then the D transistor, source to drain, to the output. If it was B and then C and E, it would go B transistor, circumvent the D transistor, and then I go source to drain on E, source to drain on C, and then to the output. So that's all of our logic combinations for what happens if you get a logic 1. But if you want a logic 0 on the output, then we worry about this pull-down network, which we have designed our path diagram here. So for ground, it's either going to go through A and B to the output. So what's going to happen is, since you have two paths, you can have two connections from ground to the inactive region, right? So that's why you see here we only have one. That's because everything has to go through one path. So here, if I want to go through A and B, it just goes A, B to the output. And so if A and B are 1, here's what's physically happening. This transistor is activated and this transistor is activated. So that means this transistor is off and this transistor is off. That means there does not exist a path from VDD to the output, which means we can guarantee a logic 0. And, okay, so you should not do that. The reason why you shouldn't do that, I mean, did you do pull up and pull down? Is that what you did? Okay, on any, when you do your take-home exam, submit them as one stick diagram because it should be one circuit. So I think let's do an in class. I'm going to come up with a, instead of doing, let's do an in class problem. So everybody can bring out, you can work in pairs, or I just wanted to see you guys. So this F equals, I'm going to copy. All right, so it is F e for those of you who can see, it's F equals the quantity, it's all negated, A and B and C or DE. Here's your assignment. Thanks for bearing with me on the Google Hangout thing, by the way. I was improvising at the last minute.
Pulldown Network.
Oh, and yeah, and draw a stick diagram. Now, one thing I'm noticing is a lot of you are drawing your pull-down networks separately, and that's fine initially. But you want to make sure everyone involved and going to be one circuit. So that's correct for pull down. So eventually, yeah, it's, you know, it's like drawing a knot and forgetting to put all the resistors or anything on the just having them separate.
So do you, what order would be like easiest?
Yeah, well, that's why you do the, okay, so the question is, when you're doing the stick diagram, how do you know what order is easiest? But that's why I have you guys do the path diagram. So that way when you see the paths, you're gonna see a pattern emerge, and that path, so that pattern is going to be the simplest way to do it. So far from what it looks like everybody is getting the pull up and pull down networks correct. Doing the parallel and series part. That's correct. That's right. What you guys have is right. That's what you have is right. And Matt, let me double check.
Yeah, that's, yeah, well, Jason actually did something simple like this. He actually kind of as long as they're connected somehow.
When I do it, I like to do the pull-up network first and have a V out, and then do a pull. Like you see how, remember how I did it in the video? That's how I've done that. So while you guys are working on the stick diagrams, I'll drop the solution here, which you pretty much all got. Yeah. Hold on. No, D, yeah. Well, Stop erasing. There you go. Now they're supposed to be in D. Yeah, they're parallel over here. It's kind of a tricky one here. Yeah, that's it. Okay. Thanks, coming along in your stick diagram. So. The top one is a little complex. Yeah. Okay, so ground. No, you can go through D or E, right? Yes, you see how here D or E. So you can either go from ground through D to out. See that's what I'm saying? So it's out. So this is ground, D can be out, or A, B, or C. So you go A, B, C, out. So could you go like the first? Yes. A, C, So you mean like maybe if you wanted to have the out this way? So you have it here. Yes, you could do that. Okay. As long as the path, as long as it hits all three of the appropriate transistors. Gotcha. So the pull-up network is the one I'm going to go over with you guys. It's a little more complicated. All right, so I think everybody's starting to look at the solution. So let's go over the pull-down network first on the stick diagram. So let me control print screen that. So here's the thing. So if you're following this path diagram, this is ground here. Does everybody see what I'm doing here? So you either have to go through D and E and get to V out, or you have to go through C, B, and A, or A, B, and C in order to get out. So what I've done here, let's pick a different color. So in order to do this, you have to go from ground. This is going through E and D to the output, right? Or if you're going through A, B, and C, it has to go this way through A, B, and C to the output. Does that make sense, everybody?
There's a space on the left of the letter.
Yeah, so this is source, this is source and drain on each side, right? So this is source, drain, source, drain, source, drain. So for the pull-up network, you have 3 potential entry points, right? So if you want to go through A and get to D, the path would be A here, and then you skip past B and C to get here, right? If I want to go through D, I go here, then I take this path around and go out. Does that make sense? Does anybody have any questions about that? All right.
Is there always only one, like for each side, one like link to the output?
Well, yeah, because the reason why there's only one, well, I mean, there's there output. If you have, okay, so for example, let's say you had all zeros on the input. So here's what's going on. This is actually a really good question. So you can have multiple paths to the output, but only the pull up or the pull down network is going to have at least one path. So let's say we had all A, B, and C. So that means if we had 0, that means this transistor is valid, right? And we can go this way. Or this transistor is valid because B works. Or C is 0 because this transistor is valid and this works. And if D and E, then we can go like this to the output. Or if E is valid, I could even do this. I can go through here. So if they're all 0, they're actually multiple valid paths. And later in the course, we're going to be learning about what happens when you have different inputs and how that relates to the strength of the signal. Okay, so here's why I did what I did with, you have to be able to get, let me draw one thing here. You have to be able to, let's pick B and E are both 0. So this is where the design's a little complicated, but this is a good example problem to really show up. So let's say B is 0 and E is 0, and all the rest are 1s. So E specifically goes through that path. So B is 0, means we start out ground, we start at VDD. The gate of the B transistor is activated. So that allows us to go through this path, right? So we don't want to go through C because C is a 1, which means it's not activated. So that means, I don't know, this got deleted last time. So, but we have a metal path here, right? It circumvents C and gets to this point. And we have a break here, right? We can either go this way or this way. If we make this way, it goes through D to the output. But in this example I've given, D is actually a 1, so we can't go through it. So what's going to end up happening is it's going to go circumvent the D transistor, go to the source of the E transistor here, and then because E is 0, it'll go source to drain, and then there should be a metal blue here. All the times delete it. That takes you to this output. If it's C, then what's going to happen is, so we had path from A, we have a path that allows us to get to the B transistor and a path that allows us to get to the C transistor. And so the purpose of this path is to go get us to A transistor, right here. Does it make sense? I know it's probably lagging a split second. Okay, so then this path takes this path here. This path is this path. Would you like me all to redraw the pull-up network? I think I'm kind of getting a sense that the pull-up network's confusing people.
Yeah.
Sure. Done and done. In fact, I will redraw the whole thing. Okay, so this was V out. So following the little algorithm that I gave, this is V out. And so P, N, metal, VDD, ground, V out. And so the polys, I have them labeled in red. And if you notice over here, I have them just going a little over PNN. The reason I'm doing that, and it's a good habit to develop, is because when you start finally designing transistors, you remember that 1 lambda that the poly has to go over into the well regions. I use that to represent that. So that's just a good habit to start developing now. So pull down network in this case is a lot easier. So what you want to do is you either need to get through D and E to the V out, or to A, B, and C to the out. So the simplest way is, because I've set it up in the middle here, you can do a contact. Oh, that should be metal. This should be metal, and it contacts V out. So it's either going to go through A, B, or C. So you start here as the A, B, or C would go through A, B, and C to output. See, that's how I did that. And then the other one is start at ground, goes through E and then D to the output. And so that needs to be connected. Okay, so that's the simple part. So then we look at our pull-up network, and we see that we have 3 paths that we can take from VDD to another point. So that's between D and E. So at some point, we need to have a way to get to this midpoint, and we can start here, here, or here. And so we're going to have a contact. Whenever you do a contact, you're going to automatically bring it down like so. So this here, going from here to here, is the A transistor. Josh asked that question a little earlier about, so that represents the source and the drain. So what I need is a path from this contact to that contact, because that allows me to go through just the A transistor and allow it to be valid. Does that make sense to everybody? Now, same thing. I start at B, which is this one here. I go through B, source to drain, and then I want to get around C. So I do the same thing. I connect it there and hook it here. Now, what's the difference between what I just did and what I demonstrated yesterday as a fault? Remember this? Let me move the epic pen. See this right here? I said this is an error. So you're not able to there's no unique path here. Here, the reason we can guarantee it's a unique path is because of the values that we're putting on the source and the drain. So if we only want to go through B, so in this case, the pull-up network, B is 0, C is 1, and A is 1. That means this transistor is off, so nothing can flow through, right? We're able to flow from B to C, and then the C transistor is off, so that means we want to start flow like that. If we have A is 0, B is 1, and C is 1, what we want to do is we would go through the A transistor, like so. B is cut off, so we go through here. If we tried going through C, well, C is cut off, so we can go through there to this point. Yeah, James, do you have a question?
So, I guess I'm having a hard time understanding what the difference between the two.
To two what?
The inner and the non-inner.
Okay, so here, let's say I have a flow here. I can go here, A and out, right? Or I just go there and out. This is a short. This is not a short. This is a path, right? So that means you can, maybe I should be a tad more clear. When you have in between the ground and the inactive well, remember the rules that we had, those lambda design rules? And you notice how I have it here between the P well and the V out? What you're going to eventually, this is actually a good question. It's a little bit of a, when you get to transistor sizing, you want these paths to be beneath the P active. So what's going to happen is this is going to violate all the rules and it's going to create a short. Whereas here, since it's between the P active and the V out, you're able to actually stretch the transistor. So this is not, these are actual paths, whereas this, you can't guarantee the flow here. So let me scroll down to where I had the empty white space. All right, so now, does everybody understand this portion of the path that I've done? Anybody have any questions? All right, so now our next goal is we have to get to V out, right? And our V out, we have to either go through D or through E. So you can do one of two things. If you do, you can either have it just go through D and go to V out, like so. In that case, you would have it come around here without any connections. And then what it could do is it would follow here, circumvent the D transistor, go through E, and go to the output. Or if you wanted to just circumvent D, you go like this. Oh, step one, draw it properly. So this would be our D transistor here. And then we would have B. See there, right? So you can circumvent D, go to E like that. But the more common way to do it is the first way I showed it. Would be like this. Have it go through D, circumvent E, make sure I got the pen going here. Up, D, to out. Sorry, hold on. I meant this. Because now what happens is if you have E is 0 and C is 0, for example, you go like this. You go through C, you go through this transistor here, you circumvent the D transistor, you go through the E path to your output. Does anybody have any other questions about that? All right, so that is the solution to that. Okay, so let me pull this up here. So now I also have a carry look ahead adder. So this is actually what if you remember from 385, I told you about a carry look ahead adder where you use this, you're trying to, instead of just doing carry select, you're actually trying to take advantage of the propagation properties of addition to try to be able to make it run faster, but the trade-off is that you get more size. So what's going on here is that this is the logic for it. It's not G, so then you just put an inverter over here. So it becomes G or, generate. G and P stand for generate and propagate. Okay. So now what's happening is when we design it using our and or logic, we notice a pattern emerge, right? Start seeing like, parallel, series, parallel, series, parallel, series, and it actually works out really nice. So then what you end up actually noticing is, now if you're just trying to get through the output, we got ground G3 here. So then it's, so your output. Same thing, VDD, P3, it's just PDD, this should say V out. So I go up to P3 and then G3 to your output, right? Just like so. But then if you have to go through G0, you have to then go through G1 and G2 and G3 to the output. Okay? So then you go through, but see how you're skipping all the P's, the propagates? So then what happens is you're through G0, skipping propagate, G1, skipping propagate, G2, skipping propagate, G3, the output. Does that make sense? Does that kind of clarify paths a little further? Same thing. If I want to go through G0 and P1, then I also have to go through P2, I have to go through P3 to the output. So then we follow the same thing here. It goes through, this is G0 and P1. And then I'm like, I don't want to go through G1. This is G1 here. See, I don't want to do that. So we go through P2. And here is source and drain of P2. We skip generate 2, which we don't want to do that one. Then we go to P3, which we do. And that takes us to our output. So if you're still struggling after looking at the in-class thing in 1.7, looking at this part, and this is not an example question, but this is a good way if you're reviewing and really trying to understand path diagrams. This is a really good way of, this is a good example of showing you precisely how they work and lay out and why they're important. So. All right, so since nobody has any questions, let's kind of go to this concept of pass transistors and transmission gates. Zoom in a little bit here. Okay, does everybody see all of the words? I haven't actually done. Can everybody see this whole thing? Pass transistor is an instance where an NMOS or Pmos transistor is used as an imperfect switch on the screen.
Yeah.
Oh, I mean when it comes up. Wait a second. Okay, good. I want to make sure because I know we had that issue before. All right, so what is a pass transistor? So a pass transistor is kind of just, you have a normal, let's say, so this is an NMOS, and we use the gate, source, and drain. And so this is source, drain, and gate. And we're going to define it as an instance where an NMOS or PMOS is used as an imperfect switch. Now, why would I say an imperfect switch? Any ideas? Yes, very good. Exactly right. So this is a Pmos transistor. So the idea is we want to be able to pass, like we're trying to put a VDD on source, right? And get it on the output. So it's very good. That means we want to put a 1 there. So but what happens if we put a 1 here? Let's go back to the physical implementation. If we put a 1 on the source, well, that means we are putting we're putting a bunch of holes, right? And we have a N-type source and drain, right? So are we going to get good flow through there? No, because they're going to want to stay put. So same thing with Pmos, except all the numbers are flipped. So what ends up happening is we have one instance where it conducts very well in zeros, passing zeros, and we have another instance where it passes the ones very well. So by putting them together in this concept of a transmission gate, we can actually develop a very good switch. So if we put them together like so, if G is 0 and GB is 1, what's going to happen is we have our imperfect switch situations where it's not good. So the switch is off. They're both, so it's strongly off. But then if we have the opposite situation where G is 1 and G bar is 0, well, that's the exact same situation we had when it was like a inverter. So you had an inverter and you had a 0. If you had a 0, it went good on the Pmos and it went bad on the NMOS. So if we have a 0 and a 1, that means they're both strong. They're both in that strong situation. We've avoided the imperfect. So we actually can use this transmission gate as a way of actually, as kind of a stronger switch. And they actually go forward and reverse. I think somebody asked me the question about, does it matter where the source and drain is? The source and the drain is basically how you're dictating the flow through the circuit. And if you control these well, you can have some really cool power consumption properties. We'll go over that later, but I did my whole dissertation work on transmission gates. So it's pretty neat stuff. Do you see this concept here? If you put them 1, if you do 0, now this is why we can say both strong 0 and strong 1. I should cover this before we move on. If it's a strong 0, what we have going on here, so we have a 1 here and a 0 there. We put a 0 here, which transistor do you think it's going to flow through? The NMOS or the PMOS? If I put a 1 on the NMOS and a 0 on the Pmos. So now it's in that instance where we wanted to flow through, but I have a 0 on A, meaning 0 is on the source for both transistors. What's physically going to happen? Why? That's correct. Why? Okay, so that's type. So basically what's going on here is you have them together, and your NMOS is going to, you have a 1 and a 0 on Pmos. So you won't have your N-type wells, meaning your Pmos, sorry, your NMOS transistor, and your P-type source and drain in your Pmos transistor. So you want so you have both full pushes, so you want to create that flow of zeros and ones. So you want that channel 1s to flow through your Pmos, and you want a channel 0s to flow through your NMOS. So what's actually happening is you have this cut off from 1s, and it's actually going to go that way through the NMOS transistor. I know it's lagging a little bit, but in the opposite way, we have a 1 and a 0, like we're expecting, and we put a 1 on A, and that's this situation here. What that means is we want the holes to flow through from source to drain, which we can do through the Pmos transistor. So that means the opposite case allows our Pmos transistor to work. Does that make sense to everybody? Now, this is why I was so heavy on the chemistry the first couple of days. The chemistry, because that becomes really important to everything else with the flow. If you're ever confused, think back to use transmission gate and the inverter to guide you. So the inverter, right? So we have our Pmos and our NMOS, right? And so let's compare both of these. So if I have a 0 on the input, right? That means our Pmos is activated because we're putting a 0 here, which means we are pushing our electrons in the end well down, which allows us to have the flow, which means we're able to go through here. So if we put a 0 on the Pmos here, it allows us the same thing. Here, if you have a 1 on the NMOS, that pushes your P types down and allows your N types to flow out. Same thing if you have a 1 here and you put a 1 on this input, you're going to get a 0 to flow through there. So if you put those together and compare them and understand how the flow is going through, so you're comparing TGO 1.22 and let's go back all the way up to, I can do Control F, inverter. This one, 1.12 and 1.22, if you compare both of those, you'll have a really strong understanding of how those two work. And in fact, if somebody actually, if you're, here, I'll even say this, for extra credit, type up a paragraph and draw a diagram comparing 1.12 and 1.22, describing why Pmos and NMOS can work this way. Oh, that'd be a couple, successful completion will be worth 2 points towards exam 1 grade. 3. So compare those two, describe it, draw it out as the because eventually think of it from the perspective of you're in a job interview and somebody's asking you to describe CMOS and you're not preparing for it. So all this whole course now is basically trying to give you opportunities to try to work on presenting this and getting it, and explaining it to yourself. Can you prove to yourself that you know it? Because I can test you and then you can learn everything and brain dump it the moment the exam's gone. But if you're in this class, that means you should be trying to learn it past. My goal would be you should be able to pick up your TGOs and go, oh yeah, and then crush an exam with minimal preparation. All right, so that's me basically doing what I just asked you guys to do, so great. So D latches, you guys are familiar with D latches, right, from your other logic classes? So what you have going on here, if you remember, a D latch is basically just an SR latch with a D input. So this is now you have your pass transistor, right? Your transmission gates here. You're using these to control the input and the flow of the sequential logic. So your clock and clock bar. Oh, okay. So, all right, so I'm at 1.23. Well, the thing is also it'll save it on YouTube. So eventually you can all see it again. The internet's algorithm didn't do a very good job. So anyway, so D latch is a latch where the inputs are controlled by one signal. Let me use proper grammar. So you would have in an SR latch, you would have a set and reset signal, and where in this case the D signal is controlled by your clock and clock bar, right? So again, we either want to have a switch go in or not go in. So if clock is equal to 1 and clock bar is equal to 0, that means our D signal flows through here, right? And we have an inverter, so Q and Q bar. So whatever and then we put our signal here. Now notice how these are inverted. The clock is on Pmos here, and clock bar is on Pmos here. So when the clock signal switches from 1 to 0 to 0 to 1, here's what's going to happen. So you put a 0 and 1 here. What's going to happen is this becomes a 1 and a 0, which means that the value of the signal is preserved. So that is how you get your sequential element. And so for those of you familiar, if you have two inverters in a loop like that, that's very close to an SRAM circuit. You don't worry about word line and bar line. So notice how 0, Q and Q bar, because once it's passed, you actually have your Q signal here. So then you have your Q bar, and then once it loops, it's actually inverting, and it'll have the transistor working, and you'll be able to continue to hold the signal. And so here you can actually use these to, you can, if you have the transistors like so, this is actually logic equivalent to a multiplexer. So these are the same circuit. So a mux with a, if you have a NMOS, PMOS like so, let's call this clock, and we'll call this clock bar. I'm sorry, that should be A, and that should be B. So if you set them up that way, it actually does multiplexing. So if you remember from how we covered this in 235, where we had a multiplexer that was a more complex circuit with AND and OR gates and inverters, because you want to achieve that logic, and you did it probably with a K-map. Well, in CMOS, you can actually get this down to 4 transistors, which is actually smaller than an AND gate. An AND gate requires 6. So if you size it the possible way, you can actually use this to significantly reduce the size of your circuit, which, going back to this portion, here you have these 2 transmission gates. That is logically equivalent to a mux, right? And you'll also see it in diagrams in this way, where you have these switches, because either this switch is going to be on, or this switch is going to be on, or this switch is going to be off, or this switch is going to be off. And so this is the clocking diagram. Basically, going to give you the idea. So you're going, if D goes from 0 to 1, right? Nothing's really happening in Q. It's holding the original signal until clock switches from 0 to 1. When clock switches from 0 to 1, what's actually happening is, so now you have clock from 0 to 1. So now clock is 1 and 0, which means this switch is turned on, so you can get D to the Q and Q bar output. So you're gonna, it's gonna get a little bit of timing delay, which we're gonna learn about, and it's gonna follow this. And then when clock is high, and when D switches from 1 to 0, the Q bar will switch almost immediately, because it's now driven by this. So then what happens is, if when clock is 0, whatever that D value is, I'm sorry, whatever Q initially was, it's going to stay that way. So no matter what you do to the D input, you're not going to be able to change it, because both of those transistors channels are turned off. Teaching a class in a pretty much baking room. Yeah. Because everyone's starting to drag a little bit. And I kind of just, D flip-flops, you basically have, it's a 1.24, if you recall. In this case, you basically just have 2 D latches put together. except you're actually changing how the switch works, right? So in the original, you had this D latch, and you had clock bar and clock, and clock bar and clock. We see this is an NMOS, and this is a Pmos transistor. If you go to the second one where they're hooked up here in the middle, see how this one's the opposite? And see, this one's the opposite too. So basically, now you're just using switches and the sequential property of inverters to be able to control the flip-flop.
Out of morbid curiosity, I'm curious how much is this? It's like 15, 20 seconds. Okay.
That's good for me to know. Next, when I prepare for next lecture, I'll have plenty of 15-second delays to kind of, I'll ramble for 50 seconds about certain things while it's loading. Oh. All right, so what was I gonna say? All right, so and then basically this is a layout from the textbook, and it's basically you got two latches and an inverter here, kind of controlling everything, and this is the layout from the TGO, and then you can see how what I was basically describing is in this part B here. And this will show up in 15 seconds or in James's 3 seconds. But see how this one's on and this one's off, and this one's off and this one's on. So then you basically want to be able to create this situation. Then when the clock changes, you now are holding the value here and it's passed on to the next one. So you're going to have the opposite value, and that's where you get the flip-flop property. And down here at the bottom, so while it's describing that on your screen right now, there's a clock diagram on the bottom that you can see. And so you see how it changes to 1, and then your D changes, and then your Q is here, and then it's holding and holding and holding because it has to happen twice while clock is 0 to flop. So that's where you get the flip and the flop part. So I think this would be a good place to stop because we're going to start going into the basics of Verilog starting next lecture. So we'll stop at 1.24 so you can do the TGOs. And I would highly recommend, since it's not a very heavy assignment, to that extra credit assignment that I gave, I would highly recommend you take up on that and practice it. I mean, you're allowed to work together on these. My attitude is you guys are juniors and seniors. You've been through, I call 385 to prove to me you're an adult class. So after this point, it's, you know, we're now prepping for your career. So work together on this. If you want, you know, go down to the lab and grill each other. Why does this work? Why does this not work? And explain that. You know, be practicing it. I want you all, I think I gave all A's and an A- last year in this class. I have no real interest in giving anything lower than a B unless you do something royally stupid. So don't do something royally stupid. Does that give you an idea of kind of what I'm expecting from you guys in this course? Okay, lady and guys, I don't want to be rude. In that case, let me end our little hangout and